All right, welcome back again, everybody. Today we're doing section 1.4, and I'm really excited about this section because this one is all about the theory of approximation. This is one of the sections that distinguishes this course from like a standard pre-calculus course. Approximation is just a really critical concept in modern math and science, and it really behooves us to spend a whole section on it, a whole day if we can. And you'll see why as we go through. So let me pull up the slides and let's get started. So this section is all about the theory of approximation. We're going to get some motivation for why we are spending time on this. We're going to talk about the difference between equalities versus approximations. We're going to talk about a very special function called the absolute value function. We'll get into the nitty-gritty of functions in chapter 2, but for right now, we need to discuss this particular function, the absolute value function, which I'm sure you all have heard about, but we're going to delve in a little bit deeper today. We're going to talk about properties of that function. Then we're going to talk about absolute value and distance. And this is actually one of the more critical concepts from this section. You're going to need it a lot when you get into Calc 1, Calc 2, Calc 3, and just beyond the notion of absolute value and distance. Then we're going to discuss errors because errors becomes an important point of focus in math and science. And then at the end, I'm going to leave you with a little taste of some intriguing mathematical ideas on the mathematical horizon. One of them is called Diophantine approximation. All right. Okay. So let's start with this. Let's get some motivation for why we even care about approximation. Turns out that many of the results in calculus and every STEM field really have a lot to do with the theory of approximation. So approximation theory is just the study of how mathematical objects can be approximated with simpler or more fundamental objects. That's what it is at its core. And a lot of times, what we want to do when we approximate something is we want to analyze the error associated with an approximation, right? um, the objects that we actually use in an approximation can be very different in type. So the theory is actually very general in nature, and it's got a lot of wide-ranging applications. In a very direct way, the primary objects of study in the calculus sequence are the results, we call them the limits, of certain approximating objects. So what you're going to see when you get into Calc 1 and Calc 2 and Calc 3 is you're going to basically construct these approximations and you're going to make them better and better and better and see if these approximations converge to anything that is an exact value. That's pretty much the study of calculus for three whole sections. Sorry, three whole courses. So, for example, in Calc 1, you're going to approximate the approximating objects you're going to use are secant lines to a curve. We'll talk about those later. Quadratures to the area of a region, or polynomials to non-polynomial functions, right? So this is like what's coming down the pipeline in your next couple math classes. And then beyond calculus, there's a lot more use of the theory of approximation and the efficacy of approximation methods. It's an active field of research currently in every STEM field, in particular computer science and physics and biology. But I'll say this, computer science majors, you will study the theory of approximation a lot. A big reason for that is computers have to terminate their processes. They cannot go on forever. They cannot understand infinity. They cannot see things like the number pi, the number square root of 2. Well, I take that back. They can see algebraic numbers, but they can't see transcendental numbers like pi or e. And so what they do is they create finite approximations of these numbers. And a big question becomes, how good is that approximation, right? How good is that approximation? So why should you care? Here you go. A primary motivation for the study of calculus itself is that it enables you to analyze deeply and rigorously how good an approximation is. So your real question should be, what do I want to approximate? And how good does my approximation need to be? How good does it really need to be? Can it be, do I just need it to be accurate to the ones place or the tenths place or the hundredths place? Do I need accuracy up to 29 digits or 100 digits? These are relevant questions, and these are what you're going to talk about in computer science in particular. So speaking to modern considerations, in the year 2025, machine learning is literally the study of the theory of approximation. That's what it is. That's literally what it is. You can follow those links and read about it. Perfect example for modern times are large language models like GPT-4. If you use Chat GPT, that's a large language model. And here's the thing about those things. They are just approximators. They're an example of what we call a universal approximator. They're not doing anything exact, and they're not actually computing the math. If you ask ChatGPT to do a math problem, it's not actually doing the math at all. What it's doing is it's computing an approximation of the answer you want to hear. And it's trying to get a really, really, really good approximation, an approximation that is so close that you can't tell the difference between the approximation and the exact value. That's what it's doing, all right? Um, yeah, it's a machine that approximates a desired result to some degree of accuracy. Now, if you want to know how good an approximation is, then we need some relevant and consistent notion of distance between the thing being approximated and the things we are using to approximate. And we need to find a way to determine that distance, right? So we basically think about it like this. We've got an exact value and we've got all of these approximations, right? That might be they might be really off. They might not be good approximations at all. So here's this exact value, and we got all these approximations. How close do these approximations need to be before maybe the human eye can't tell the difference? Or before the application for which we are using this theory doesn't need to be any more precise than that, right? We want to be able to answer that question, and that becomes a main focal point in your upper division courses. So in order to build some fundamental intuition for this theory, we're going to return to the real numbers for a minute. Remember, we like to play with numbers because they're easy to work with, but all of this can be applied more generally. And we're going to introduce what's called absolute value. But first, a very, very important note. Approximations are not equalities, okay? You will hear me say this a lot, and I need you to take this to heart, and I need you to believe it. In fact, I just want you to think about this for a second. Where is the thinker? Okay, okay. Think about this for a second. Think about this box, what this says, okay? And now I want you to say it out loud to yourself 5 times. There you go. Say this out loud to yourself 5 times so that you remember approximations are not equalities. They are not exact values. Well, I should say they're not the exact value that we're looking for, but they're not equalities, okay? So another important point is this, and I always tell my students this, don't round or truncate or approximate anything frivolously. I'm a little bit biased because I used to work in industry, and I will just say, don't approximate unless somebody tells you to approximate. Don't take the burden of approximation onto yourself and take the blame for when that approximation is not good enough. Have somebody else tell you to approximate, and then you say, okay, how close do I need to be? And you have them tell you how close they want it to be. And then you make sure it's within that tolerance, which we're going to talk about in a minute. Okay. So don't approximate unless you were specifically asked to. Um, because this is the issue. If you approximate, you lose equality. And we talked about this in the last section, right? When you approximate something, you lose equality. And what happens is you introduce an error. There's an error associated with any approximation. A lot of times we denote this error by this little symbol here, epsilon. It's a Greek symbol for E. It's just epsilon. And when you see that, I want you to think of it as an error, like an amount of error, okay? The other thing I want to say is this, kind of picking up on what I said in the last section, don't abuse the equal sign. If you've made an approximation, equality is lost. You do not have equality anymore. So do not abuse the equal sign. The equal sign is very powerful. Equal sign means this is the same value as this. If these two things are not the same value, do not put an equal sign between them. All right. We'll talk more about that in class. Yeah. So when an approximation is introduced, kind of repeating what I said last time, we use the little wavy equal sign to indicate that an approximation has been made at that point. So here's a good example. And when you're doing the homework, I need you to really take this to heart. But this is a common thing that I see with students. 1/3, that's not equal to 0.33. That's not equal to 0.33. I hate to say it, but that's not equal to 0.33. 0.33 is equal to 33 hundredths. And now that we talked about the decimal system, maybe you can see why, right? 33 and it ends in the hundredths place, that's 33 hundredths. That's not 1/3. Notice this fraction is not the same as that fraction, and they're not associated, they're not equivalent fractions, right? One is not a multiple of the other. Or I shouldn't say a multiple of the other. The numerator and denominator are not the same multiple of the numerator and denominator over here. So 1/3 is not 0.33. So do not say they are equal because they are definitely not equal. Depending on the context, they could be in a scale, right? The scale, they could be worlds apart, depending on what we need to use it for. So if we wanted to write it correctly, if we wanted to write it as a decimal, we could say 1/3 is 0.3 repeating. That's probably the most accurate way of writing it as a decimal. Or you could use the dot 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 notation. The only issue with the dot 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 notation is it can be a little bit ambiguous because we also use that to mean it keeps going. So like we could kind of write the decimal approximation of pi, do like I'm sorry, we could write a decimal approximation of pi and then put dot 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 at the end. That doesn't mean that the pattern repeats. It just means that the representation keeps going. So this is what I would recommend if you've got a rational number. That's the best way to write it as a decimal. Um, Now, what we could do is this. So if you want to say, or if you want to relate 1/3 and 0.33, you can use the wavy equal sign. 1/3 is about 0.33. You're right. It's about 0.33. Not equal, but about. It's an approximation, right? So there you go. I'm explicitly stating that we're not talking about equality anymore. We're talking about closeness. Right. Now let's shift gears for a minute and let's talk about absolute value and the absolute value function. Simply put, intuitively put, the absolute value of a real number is its distance away from zero, the origin, right? That's really what absolute value is telling you. Um, we often denote absolute value by these two bars, but that's not all. Computer science majors and even we actually will see this. A lot of times they'll just use ABS and then the little parentheses for function notation. So you might even see this, or I could write it like this: ABS of x is equal to absolute value of x. That's another way of writing it. Now, symbolically, this is actually wait, yeah, symbolically we write this. And I'm going to explain what this means on the next slide right here. So the intuition behind absolute value is it's basically telling you the size of a number, the size of a quantity, its exact magnitude. The way that we define it is through what's called a piecewise function. We're going to discuss those in chapter 2, but for now, you can basically think about it as a function where the rule, the thing that the function does, changes depending on what you put into it. Maybe as a little flash forward, a function is basically a rule, and the rule says what to do to the thing you put into it, right? Well, the absolute value function says, hey, it depends on what you put into me. So if the thing you put into me is greater than or equal to zero, I'm just going to spit that thing back out again. However, if the thing that you put into me is negative, then I'm going to take the opposite of that thing. And that is exactly how the absolute value function makes everything positive, right? Well, if the thing you put into it is negative, the absolute value function takes its opposite, but the opposite of a negative number is positive. Sorry, did I do that right? Yeah, absolutely. Wait, yep, that I get it backward. The opposite of a negative number is positive, and that's how the absolute value function works. So, for example, the absolute value of 8 is 8 because 8 is greater than or equal to 0, right? So this rule applies. Now, the absolute value of -2, it's not some magical box that just like says 2. What it does is it goes through a process and it says, wait a minute, -2, that's less than 0. So I'm going to take the opposite of -2. And the opposite of -2 is +2. So this is how the absolute value function actually works. I know a lot of teachers will skip this intermediate step, but that intermediate step is the most important part. It's literally the thing that shows you what the absolute value function is doing. It takes the opposite of negative numbers to make them positive, and it just spits positive numbers back out. No need to change them. All right. Okay. Now let's make some more sense of this. We're not doing any algebra here. We're just using the intuitive understanding of absolute value. Why is absolute value of -5 equal to 5? Simply because -5 is 5 units away from the origin. Let's count. Here's the number -5. Here's the number 0. How far away is it from 0? 1, 2, 3, 4, 5. It's 5 units away from 0. So the absolute value of -5 is 5. All right. Okay, now we got to talk about some properties of this function. So this function has some really nice properties. It's basically properties that you really wish it could have, and the good news is it has them. The first one is this: the absolute value of a negative number is the same as the absolute value of its opposite. Excuse me. The absolute value of a product is the product of the absolute values. That's a really special property. Not many functions have that. We call that multiplicativity. Multiplicativity. Not very many functions have that property, but the absolute value function does. There's this one. If you take the absolute value of a power, that's the same as taking the absolute value of the base and then raising it to that power, excluding 0 to the 0 situations and funky situations like that. You'll talk about those more when you get into Calc 1 and 2. But that's really nice. You could almost think of it as you can pull the power out of the absolute value bars. That's like symbolically what's happening. And then maybe this one is kind of funny or trivial to state, but the absolute value of the absolute value is just the absolute value. So it doesn't change anything when you take the absolute value of the absolute value. Okay. Now, why is this type of thing important? Well, we're going to get our first very important theorem here. In this section, this is called the triangle inequality. And I'll say this, math majors, especially analysts, this is going to be your bread and butter later on. This is a very powerful result. Let me state it, and then I'll give you some intuition for it. So let x and y be real numbers, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y, less than or equal to it. So I just kind of want you to stare at this and think about it for a second. Okay. Um, and let me try to explain it in a different context, but let me read this note first. The only time that equality will occur is when both x and y are positive or both x and y are negative. Okay. Um, or I guess if they're both zero, right? They're both zero. So in other words, when they're in the same direction. So if x and y are both positive, it'll be equal. When they're both negative, it'll be equal. But that, yeah, they got to be in the same direction. This becomes a lot more meaningful when we talk about vectors. And so pretend we're not working with real numbers yet. We haven't talked about vectors until the next section, but maybe a geometric way of thinking about it is if you've got the vector x and you've got the vector y, right? Ooh, sorry, I don't want to do it like that. Let me do it like this. Y. There we go. Okay, so this is like traveling along a direction, an arrow to a point. So if you go, oh, geez, sorry. Let me try this again. Let me make it a little better here. So let's say this is x, and let's say this is y, right? So going along x and then going along y is kind of like doing this, right? Or you could go straight from this tail to that tip. That's the sum of those two vectors. That's basically doing this. So what this is saying is going along x first. Hey, come here. Going along x first and then going along y will always be a greater distance or equal to going along straight from point A to point B like that, or point C, I should say. Yeah, we'll talk more about that later, but that's the vector interpretation of it. Okay, now we got to talk about distance. And this is one of those definitions that is going to be absolutely critical for you to understand in Calc 1 and Calc 2. So, settle down. commit this to memory and make as much sense of this as you possibly can. It's going to help you a lot when you get into calculus. So the distance between two real numbers, A and B, is the absolute value of their difference. Okay? Now I want you to just think about this for a minute and ruminate on it for a moment. Okay, now I want you to say it out loud. I want you to read this out loud to yourself and try to say it in your own words. Say it in your own words, okay? Okay, now do it again. Say it again and think about it a little bit more. The distance between two numbers is the absolute value of their difference. It's the absolute value of A minus B. Okay. All right. Now, you'll see even more why that's important when you get into Calc 1. We're going to see it right now, but you're going to see it explicitly when you get into Calc 1. So in other words, the distance between two numbers is the absolute value of their difference, right? So we're taking their difference and we're taking the size of that difference. That's really all it is. Now, again, we're not doing any arithmetic here. We're just using the definition of absolute value and the definition of distance right there. So think about it like this. The absolute value of 9 minus 3 is equal to 6 because the distance between 9 and 3 is 6 units. All right, let's look at the picture here. Here's 3 on the number line. Here's 9 on the number line. Let's just count how far apart they are. 1, 2, 3, 4, 5, 6. So the absolute value of 9 minus 3 is 6 because the distance between 9 and 3 is 6. That's the idea. All right. Now, of course, if you perform the subtraction, right? If you do 9 minus 3, you get the absolute value of 6. Absolute value of 6 is 6 because 6 is positive. That also works, right? Okay, let's do a sum. Now, this is a cool trick that you're going to see happen a lot in mathematics. We're going to rewrite this sum as subtracting a negative, okay? So we're going to write it as minus negative. There you go. So 7 plus 10 is 7 minus negative 10. Now, interpret this as a distance. Interpret it as a distance, right? So here we're saying the distance between 7 and negative 10. How far apart are those two numbers? Let's count. Here's negative 10. Here's 7. Let's just count from negative 10 to 7 and see how far we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so the absolute value of 7 plus 10 is 17 because the distance between 7 and negative 10 is 17. There we go. That is what that symbol means. That's what this symbol means. Okay. Now, what's really cool about this distance interpretation is this. I'm going to rewrite absolute value of x as absolute value of x minus 0. That's allowed. I just added 0. I haven't changed anything. The value has not changed. But look, now we can interpret this as a distance between two numbers. This is the distance between x and 0, which is exactly the definition of absolute value, the distance between x and the origin, right? There you go. So it's the same thing. Okay, now let's see why this can be helpful. And this is one that I want you to try on your own. So think about this for a minute first, right? So think about this first. What's the distance between 15 and 61 divided by 4? Think about it. Okay, now I want you to say something out loud to yourself or to your dog or to your cat, to your friends, to your brothers, your sisters, about what you think this distance will be and why. Right. Now I want you to try to work it out on your own. See if you can compute that distance. And I'll give you a hint. Find oh, maybe I'll give you this hint. Write 61 over 4 as a mixed numeral and see what you get. Okay. Now let's work it out together. So the hint I gave you was kind of a big one, right? Let's do that division. Let's compute that. So what we need to do is we need to compute this, the absolute value of 15 minus 61 over 4. But we can rewrite 61 over 4 as a mixed numeral, right? We do the division algorithm, we get 15 with a remainder of 1, so 61 over 4 is 15 and 1/4. So now we can rewrite this like this. We can rewrite it as this is equal to this. And now this is really easy because we're finding the distance between 15 and 15 1/4. How far apart are those two numbers? 15 and 15 1/4. They're a quarter of a unit apart. There we go. And that makes sense, right? Because 1/4 is the fractional part of 61 over 4, and 15 is the whole part, the integer part, right? So maybe this kind of gives you a flavor of why we like this notion of distance and absolute value of a difference, giving us the distance. We can kind of see how far apart two numbers are. And when they're really, really close, we want to see how close they are. That's the like the moral of the story there. Okay, now, here is an interesting one, and I want you to try this on your own, but here is the catch. I do not want you to do any algebra. I know some of you have learned how to solve these types of equations. Maybe when you see this question, for what number is x, does x minus 4 equals 9? Maybe you're like, oh, I remember these. That's okay, you're in good company. But I don't want you to do algebra here. I want you to use the definition of distance. So this is one I want you to think about on your own. So let me throw up the thinker. Think about this for a second. Okay, now say something out loud to anybody, to yourself, to nobody, but you got to say it out loud. And I'll give you a hint. Express this in terms of distance. Okay, now I want you to solve this problem. So I want you to come up, or I want you to figure out what are the numbers where this is true. Don't use algebra, use distance. Okay, now let's do it together and hopefully you'll see this magic here. All right. So for what numbers x does x minus 4 equal 9? Well, let's state it in terms of distance. That was my first hint, right? So what this is really saying is the distance between x and 4 is 9. So the distance between x and 4 is 9. And those are the numbers that solve this problem. We need to find what numbers are 9 units away from 4. There we go. What numbers are 9 units away from 4? And that's the answer to that question. Now let's draw a number line. So here's the number 4. We're going to put that right in the middle. And we're just going to count 9 units away. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. But we could also go the other way, right? So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then our answers are -5 and 13. So the answer to this question is -5 and 13. Those are the two numbers where the absolute value of x minus 4 equals 9. Wild, huh? That's it. That's what that symbol means. You can do it without algebra. This doesn't need algebra, it just needs understanding the definition of absolute value. Okay, now we could use algebra, so let's explore the algebraic way of doing it. Let's use the definition of the absolute value function, and then let's solve for x. Now remember, there's two possibilities when you have an absolute value, right? The absolute value function splits into two different things. It's not just one thing, it's two separate things. So here we go. We're going to first directly apply the definition of absolute value, and we're just following our nose here. We're not skipping steps, we're not jumping ahead. Just go one step forward. So, and just to remind you, remember, where is it? Where is it? Where is it? Lost my, this thing? Okay, so we're going to be very, very straightforward and plain here. Absolute value of x is x if this thing's positive, or the opposite of x if this thing's negative. Everywhere you see an x, replace it with whatever's between the bars. That's how these functions work. Everywhere you see this x, we're now going to replace it with x minus 4. And we're going to get two cases. So let's go back to our problem right here. Okay, so two cases. Either this thing is equal to x minus 4, or it's equal to the opposite of x minus 4. I'm not skipping steps, one step at a time. Now let's proceed. We need this thing to be equal to 9, so our two cases give us x minus 4 is equal to 9, or negative x minus 4 is equal to 9. And now we can solve the equation for x. Boop, boop, we get x equals 13, or boop, boop, x equals negative 5. Same result. One result uses intuition, distance, and geometry. This result uses algebra. That's why algebra and geometry are BFFAE, because there's an intimate connection between those two things. All right. Okay. Now that we've talked about absolute value, we've talked about distance, we need to talk about errors. So like I mentioned a bunch of times, anytime you've got an approximation, there's a difference between the value of the approximation and the exact value being approximated. There's a difference there. And we call that difference an error. Okay, that's an error associated with the approximation. Very often, we want to know the size of that error, the absolute value, and most of the time, we want that error to be very small. How small is a big question. That's a question that has infinitely many answers that completely depends on the context. So again, engineers, computer scientists, physicists, you will be asking this question a lot. How big is the error? How big are we allowed to have that error be before our results are not useful anymore? Okay. Now, in industrial applications, the minimum size of the error is often called a tolerance. You can literally think of it as like what you can tolerate, or like what this application can tolerate. And if you go beyond that tolerance, everything breaks. So you can't go past that tolerance, right? And again, we often use epsilon to denote a small number or error. Now, let's make this a little more mathematical. Hopefully, the idea is starting to make sense. Exact value, approximation, difference between the two, the size. There's an error, right? There's an error. A lot of times we have a minimum error that we're allowed, and we call that a tolerance. So mathematically speaking, it's going to look like this. If we have some exact value L and some maximum error or tolerance epsilon, which is some positive number, then we want some approximate value x such that the distance between the approximation and the exact value is less than the tolerance. Okay? Now, I want you to ruminate on this for a minute. So just think about what this says. Okay? And then I want you to say this part out loud. Give your brain that feedback, or say it to your friend, or if you're watching the video with somebody, say it to them. Talk to each other about this, or talk to yourself about this. Okay, let's talk some more about this. So, looking at this symbol for a minute, what we're really saying is that the distance between the exact value L and the approximation x is strictly within tolerance E, epsilon, sorry. Right? Now we're going to do a tiny bit of algebra, but we're just going to use the notion of distance and differences again, right? So here we're saying the distance between x and L is less than E. Well, that means that the difference has to be less than epsilon or greater than negative epsilon, right? Differences could be positive or negative. Positive numbers are bigger than negative numbers, so that's why you get this order relationship. And this is what we're saying. Now we can isolate x in this compound inequality, and we get this. This is saying that the approximation has to be strictly between the exact value minus the tolerance and the exact value plus the tolerance. Our approximation has to lie in between those two numbers for it to be useful to us in whatever our application is, right? In practice, we usually want epsilon to be very small, but here is a visual depiction of what this is saying. In fact, these are all saying the same thing. This is equivalent to this, which is equivalent to this in picture form. So here's L. Oh, wait, I have this on the next slide. Let me do this. Here we go. So this is basically giving you that. It's equivalent to that. So intuitively, L is like the ideal goal. That is the perfect exact value. That's what we wish we could get, right? But our approximation x could be a little bit above or a little bit below, and we would be okay with that, right? In practice, in industry, in application, nothing is exact. Nothing is exact. There's always some approximation going on, but it has to be within a certain tolerance, and that tolerance is epsilon. So here's what we really wish we could get. This distance here is epsilon. This distance here is epsilon. That's how far off we're allowed to be. And then these are the lower bounds of acceptability, right? So you can think of L as the center of our attention, and minus E, L plus E are like the boundaries of acceptability. So we need X to lie within that interval for it to work. Otherwise, we got problems. Okay, here is a good example. Here's a quote word problem, right? I had to do stuff like this all the time when I was working in industry. So I want you to think about this one. But again, we're not really doing a lot of like algebra. This is not like solving for X or anything. Just try to make sense of the problem and work it out, and we'll do it together. So first, think about it for a minute. Oh, I guess I should say it out loud. Hold on. You've been contracted to make a box that has an internal width of 13.2 centimeters, and the given tolerance for the width is 1 millimeter. You're allowed to be 1 millimeter off. My question to you is, what is the smallest the interior width of the box could be? And what is the largest the interior of the box could be? Okay, now think about it. Okay. And now say something out loud to yourself about it. You may even just repeat it. When you have word problems like this, read it two, three, four, 5 times, as many times as you need to make sense of it. Okay, now I want you to try to work it out on your own. And the hint I will give you is consider the units involved. Okay, now let's work it out together. So here's how I interpret this. I say, okay, we need to make a box that has a width, an interior width of 13.2. That's the ideal goal. That's like L, right? Now we have a tolerance. The tolerance is 1 millimeter. So we're allowed to be 1 millimeter above or 1 millimeter below this ideal measurement. One thing I notice also is this is in millimeters and this is in centimeters. So we need to convert this to centimeters. 1 millimeter is equal to zero point 0.1 centimeters. So I see that. Okay. So we can basically go up I'm sorry, we can go up zero point 0.1 centimeters, or we can go down zero point 0.1 centimeters from this value. So what I'm visualizing in my head is this. I see a point in the center, that's 13.2. And then I see another point over here that's going up zero point 0.1 centimeter. So that would be 13.3. And then I see another point down. So I need to go down to 13.1. Okay. And those are the boundaries of acceptability. Now, the thing with the tolerance is we cannot be equal to those. The tolerance is basically a strict upper and lower bound, or giving us a strict lower and upper bound, right? So the smallest the interior width of the box could be is 13.1, but we got to be a little bit more. I'll just say greater than 13.1, or we need to be less than, actually, I should say we need x to be less than 13.3. There we go. So x has to be bigger than 13.1, but less than 13.3, and then we'll be okay. The interior of the box. All right, here it is written out. Everything I just did right there in that solution is written out on these slides. I used W in this case instead of X, but W is the interior width. This is the absolute value inequality that describes the relationship. We need the distance between the exact value, sorry, the distance between the exact value and our approximation to be less than zero point 0.1 centimeters. This is the inequality you get. This is what we just figured out. And then visually, this is what the solution looks like here. W can be anywhere, the width can be anywhere between these two numbers, 13.1, 13.3. There you go. All right. Notice how I didn't do any algebra there. There was no solving for X. All I did was think about distance, absolute value, tolerances, and just the definition of this symbol right here. That's really all I did, okay? That's the power of this type of intuition. Okay, now, speaking of errors, we're going to kind of round things off now. um, If we have a number's decimal representation, we can chop off the decimal representation at any decimal place. And when we do that, we get what's called a decimal truncation. Truncation. So for example, we could truncate the number pi to the hundredths place, and we get an approximation of pi. Pi is about 3.14, right? So here, pi is equal to blah, 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 blah. But remember, pi is an irrational number. It's also a transcendental number, and the decimal representation goes on forever. There's infinitely many digits. There's no consistently repeating pattern. It keeps going. So anytime you see pi written in decimal form, it's basically an approximation. So here we're approximating it as 3.14. One thing I want to be very clear about, pi is not equal to 3.14. Y'all can ask me about how I feel about pi day when we're in class, but pi is not equal to 3.14. It's about 3.14. Plus or minus. I guess I should say plus. It's not equal to 3.14. It is approximately 3.14. So when you truncate a decimal representation, you get a numerical approximation of a number, and you get an associated error with that approximation. So that approximation is accurate or exact up to and including the decimal place just before the chop, right? And the error is equal to the tail end that was removed. So let's do that for pi for a second. What we're going to do is we're going to explore some decimal truncations of pi and the associated errors. So I already said this. Here's pi. Pi is equal to that. If we choose to approximate pi by 3, let's look at the distance between that approximation and the exact value. Boom. We just talked about this, right? This is the distance between 3 and pi. This is our approximation. This is the exact value. What's the distance between those? Well, we can do this subtraction. And what we're going to get is we're going to get the tail end. We're just getting the tail end, right? If you take this number and you cut away the 3, you're left with the tail end, right? The absolute value of this number is just the positive version of it, and that's always going to be less than 1. So when we do this approximation, our accuracy is only good to the ones place. So this would be a very bad approximation. Yeah, pi, sure, it's about 3, but it's a very rough approximation. Let's go down a little bit. Let's approximate pi by 3.1, and let's look at the accuracy there. So same thing, the distance between the exact value and our approximation. Here's that subtraction. When we subtract, we're left with the tail end of that decimal representation. And this one's actually a little bit smaller, right? Because we included more digits in our we included more decimal places in our approximation. So this is less than 0.1, right? Because 0.1 would have a 1 in that place. So no matter what this number is, it's less than 0.1. So we're accurate to the tenths place at this point. We have accuracy up to the tenths place. The difference between the exact value and the approximation is occurring after the tenths place. Wait, sorry, after the tenths place. Let's do it again. Let's approximate by 3.14. Same deal. Distance between pi and 3.14. Perform this subtraction. You get this. Make it positive, and that number is always less than 1/100th. So this approximation is accurate to the hundredths place. And then you keep going. Here's 3.141. We get we get accuracy to the thousandths place, because the only difference occurs after that, right? And you could keep going, right? This is the approximation process using a decimal approximation. So here I put it all in a table. Here is the approximation of pi that we're using. This represents the exact error. And I'm being stern about that word. This is the exact error. If you wanted a symbolic representation of what the error between this and pi is, it is this number. Whatever that number is, that's what it is. Here it is as a decimal. And then this is the accuracy, the decimal place accuracy that we have. So this approximation is only accurate to the ones place. This approximation is accurate to the tenths place. This one, the hundredths place. This one, the thousandths place. and this one the 10,000th place. So we're getting more accurate approximations the more decimal places we include. Not equal, but approximate. Okay, so now to kind of wrap things up, I know this is already a lot to digest, but on the mathematical horizon, there's this really cool theory called Diophantine approximation. So a lot of this I've already said, so I can kind of breeze through it. Notice that the approximations from the previous example, they're all terminating decimals. They're stopping, right? So all of these are actually rational numbers. So 3 is a rational number, 3.1 is a rational number, 3.14 is a rational number. So here what we have is a whole bunch of rational number approximations of pi, which is an irrational number, right? Uh, what's nice about this thing is uh, baked into this example is a very simple result. If you want to take a rational number that has a terminating decimal representation, like it stops, and you want to write it as a fraction, it's super easy. You just write this number over the decimal place that it's in. Let me zoom in a little bit there. Oop. Ah, there we go. Just a little, nope, there we go. Right, so 3.1415, if you want to write it as a fraction, you just write 31415 over 10,000. That's how you convert. If it's got a repeating decimal representation, well, maybe we can talk about that in class, but you're going to have to deal with ninths instead of tenths. I'll just say that. I'll leave it at that. Okay, so the study of how to approximate irrational numbers using rational numbers like we're doing here is something called Diophantine approximation. It's an active field of mathematical research today, right? So here's a kind of an interesting result. It can be shown that 22 over 7 is the quote best rational approximation of pi. But why? Why is that the best, right? That's Diophantine approximation. These types of approximation problems are intriguing, they're interesting, and there are people working on them right now. So if you ever wondered, like, what do we do in math research, or is every math problem solved? The answer is a big no, not even close. There are many, many, many unsolved math problems, and we're just waiting for you to join us so you can help us figure them out. All right? So that's on the mathematical horizon for those that are interested. All right, on that note, let's play. All right, I'm excited to work with you all about this. If you're taking this course with another instructor, I know they're excited to work with you about this kind of stuff. I hope you enjoyed this lecture as well. I'm looking forward to the next one, and I'm looking forward to helping you all learn these things. Thank you again, and I'll see you next time.